In a previous video, I showed how my inexpensive DC electric load blew up, and then I repaired it, and then blew up again. And since then, I've just not been able to let it go, apparently. And I've bought some more parts, I've done some more reading, and I have some more ideas about why it failed and ways that I can fix it. So what was interesting, first off, was reading that MOSFETs that you buy online are often counterfeits or fakes. They work, they just don't work to the original specification. And if you go in here into my graveyard of MOSFETs, we have the IRF 260 that originally came on the DC load. And then here's two IRF 260Ns that blew up, and two of the IRF 260Ns that I haven't used yet. And I can actually weigh these, apparently, according to what I read online, and that should tell me if they are originals or if they are counterfeit. So I'm going to do that in a moment. But one other thing that I read, and that is pretty interesting, is that the IRF 260N, of which my replacements are the new version of the IRF 260 that it came with. And some people say that the IRF 260N is a better performer in terms of performing to spec, but not overall as robust as the original. So I think both of those factors make sense in my case. I was able to blow up the replacement MOSFETs much more easily than the original. So I might as well go ahead and do the weighing test to get an idea of whether I'm dealing with a fake. The more complete test would be to test some of the advertised specifications, like the resistance between drain and source when it's all the way on. I could do that, but this is a quick and dirty. So here's the IRF P260, 5 grams. Here's one of the replacements, the 260N, 4. Here's another one of the replacements. Its legs are a little bit longer. Less was blown off of this one, so let's weigh it. Still 4. The original is clearly 5. So, and I can even measure one that hasn't had the legs blown off. Let's measure this one. So it comes in at 5. No, it comes in at 4 as well. So all of these replacements in various states of destroyed or brand new all weigh somewhere around 4 grams, and the original IRF P260 reliably weighs 5 grams. Of course, my scale isn't the most precise, so it's only giving us a whole number. But that's the first indicator. So it's a good chance that I should mention I bought these not on DigiKey, not on Mouser, not on an electronics website. I think I bought them on Amazon. So there's a good chance that these are actually not able to perform to the original specification because they probably are knockoffs. That could explain why the replacements were not holding up as well as the original, in addition to the fact that the N model may not be quite as robust as the original model. What I was able to find online is another MOSFET of the same form factor, but this one offers pretty significant improvements in important ways. Most significantly, this is called a linear MOSFET. So this is the type of MOSFET that is specifically designed for being turned on part way. These other MOSFETs that came with the load and the replacements, even if I got non-counterfeit authentic replacements, these types of MOSFETs are really happiest when they're all the way off or all the way on. They don't really like to be in that transition zone for very long. They can flip on and off really fast, or they can even flip part way on and then off repeatedly at high frequency, and that's okay. But when you flip them partway on and hold them for any period of time, and a period of time here means, milliseconds, then they are much more prone to failure. This, on the other hand, is designed for staying on all the way or staying halfway on, anywhere in between, and it has guaranteed specifications, but guaranteed performance in that transition range. The critical area to look at on a data sheet for the performance in that transition area is called the SOA, or the Safe Operating Area. And this one has pretty incredible safe operating area. It's rated at 200 volts and 80 amps, but if you look at the sort of the area under the curve in the SOA portion of the datasheet, you'll see a line, a series of lines for how much current or voltage it can handle at certain lengths of time. And then there's an extra line that just says DC, and that's the amount of current at a particular voltage it can handle continuously at a given junction temperature. So all that out of the way, the bottom line is that this is a bad mofo. This thing handles way more power, and it's actually designed to do what this board is trying to do with it. Linear MOSFETs are not very common. You kind of have to go looking for these things, and they cost quite a bit more. So whereas these were a few bucks, this was like 15. But it should perform exactly like I need it. So I'm going to go ahead and swap this MOSFET on. I'll be getting the benefit of, for sure, this is authentic. There's no counterfeit here. This came from DigiKey, and I trust them. And it's made for what I'm trying to do. And I also have one more trick, and that's this stuff. So this is heat sink thermal compound. And you can really go down a rabbit hole on this. But there are ratings out there for how much heat transfer different compounds are capable of transferring, and this was one of the better ones out there. So I'm going to try this thermal compound, which should help in getting the heat off the back of this MOSFET and onto the heat sink effectively. So it's just a matter of putting this thing all back together, just like I did with the IRFP 260Ns, and testing it out. So I'm going to go ahead and get started on that. For the side of the MOSFET that faces the board, face down here, I'm going to use some of this material. This is a stick-on thermal pad. I feel like this pad will provide a little bit more insulation, electrical insulation, between this damaged portion of the board and the MOSFET itself. The thermal paste, I'm worried could get squeezed out of the way and there could actually be contact, whereas this will actually create a physical barrier between the MOSFET and that damaged area where there's a little bit of copper exposed. So let me put this on first. And I can still see where it needs to go. All right, there we go. So then next what I need to do is figure out where this folds down. Okay, there we go. Now I'll go ahead and solder. Of course, I can't solder that leftmost leg, and that's okay because I'm going to be running a jumper anyways. Okay, and I'm going to press down, give it some artificial pressure, just like when the heat sink is on it. So now I'll go ahead and do the other side here. I believe this is the gate. These are current shunts. So these actually measure the power that is flowing through this board from positive to negative, whether that power is going through the MOSFET or not. There's also this out port here. So if you were to connect some load there, that load would be seen by these shunts as well. So long story short is this is where we want the negative power to return. So we're going to go ahead and connect on the bottom of the board the source pin to these shunts over here, and we're going to connect it on the bottom because the length and size of these shunts is tuned to be a very specific resistance so that the voltage drop across the shunts can be used to calculate the amount of current that's flowing through them. So if I attached on top, as I did in my previous video, I would probably be messing with the calibration of these shunts. So here's a nice beefy piece of silicone insulated wire. It's 12 gauge, even though it's a short distance there, just for maximum precision. I want to use a big chunky wire so there's no voltage drop whatsoever.
Hooks right there.
Okay, so at this point it should technically work. I of course don't have the heatsink on, but let's just go ahead and do some basic testing with it without the heatsink installed, just in case we need to probe anything. So to do that, I'm going to use my variable power supply here, and this will set a backstop on the current that can go through it. Okay, so there's our power in. And then of course we need to power the board itself, so let's do that. And here's the 12 volts it needs to operate. The power is not turned on yet on the input, so let's do the reset procedure. So we need to turn these down and then press this button 1, 2, 1, 2, 3, 1, 2, 3, 4. And now we do 7, 1, 2, 3, 4, 5, 6, 7. And that should be a complete reset. We're going to start small here. We'll set it to 4 volts and half an amp. So this happens when we turn on 4 volts. Okay, 4 volts, and we see 4 volts more or less on the display. The precision on this is very low at low voltage. So due to the analog to digital converter, the ADC that's involved here, it only has so many steps. And so at the lower voltages, it's going to jump from like 3.97 to 4.01. And that's because it really just can't measure anything in between those. Just a function of how this is set up. So let's set it to 5 volts. And let's actually set the current up to 1 amp as a backstop. So 5 watts is what's possible to flow through here. 5 volts at 1 amp. Of course, we show 4.95 volts. Let's see if we can dial up any current. Of course, if I dial up the current too much, it's just going to crash the voltage. My power supply will limit the voltage to limit the current. So let's see if we can just dial up a little bit under 1 amp. Okay, we're getting somewhere. Okay, so far so good. So the unit is actually working. Let's flip it off. I'm going to attach the heatsink now, and then we'll see if it really works at significant power levels. Now the pins. We're going to clean off the bottom of the heatsink with some alcohol. And we'll go ahead and apply some of this super fancy thermal transfer paste, ChipQuick TC3-3.5G Ultramax Conductive Thermal Compound, non-curing, flowable, gray. So let's apply that to the back of the FET here. It's a nice tip, it comes out really precisely. Okay, now we attach the fan. Attach one side is attached. Here we go. Okay, we're attached. You can see down in there where the heatsink makes contact with the MOSFET. Looks good. And we plug the fan in. Okay, back to where we've been before. Oh, let's see what happens. Here's my Ego battery adapter, and I'll go ahead and get an Ego battery to plug it into. That's been kind of the gold standard for blowing this thing up. Okay, fresh camera angle so you can see what's on the screen. I also added this. It's actually a piece of flooring underneath it. This is a stone polymer composite, so nothing flammable. Offers a little bit of protection just in case we do see fireworks again. So this is a 56 volt battery. Initially, this was draining at 2 amps with no problem. I saw the initial problem on the initial MOSFET that this came with at 2.25 amps. And then once I replaced it, fixed it with my IRF P260N that I picked up on Amazon, it failed at under 1.2 amps. So those are the benchmarks to compare to. Let's see how this does. So we're seeing a little bit of current registered now. Should see fans come on shortly. 25 watts already. There's the fans. Let's dial it up just a little bit more. Temperature, by the way, 23C. 30C is getting to be like a hot day. So consulting the safe operating area, yeah, they test this thing with a case temperature of either 25 or 75 C and a junction temperature of 150 C. So assuming that this is the case temperature, I don't think we have access to the junction temperature. That would be inside the MOSFET where the drain and source actually come together, the two layers of the semiconductor meet, but this is measuring the temperature basically right next to the MOSFET. So this is our case temperature. In any case, no pun intended, the case temperature of 25C, that graph shows that it should be able to maintain our 55 volts at about 10 amps. Reading the same curve on the graph with the temperature of the case at 75C, it still should be able to do 55 volts at roughly 5 amps, which is just incredible. So for what we're doing, should be able to do well over 250 watts, even at a case temperature of 75C. I don't want to get too excited yet, but just to give you some idea of what the performance of this MOSFET is advertised as. And for comparison, this unit was rated new at 180 watts. Of course, that was with a IRFP 260, and I'm sure the wattage is probably based something to do with that particular MOSFET, but potentially based on limitations elsewhere on the board here. Let's turn it up. Of course, 1.2 is where things went sideways on the previous fix. So we've surpassed the failure point of the previous fix, which was the IRFP 260N. Let's see if we can go to 2 amps, which is where it was functioning reliably when it was new. Over 1.5 amps now, sneaking up on 100 watts, ready to rip these cables apart if needed to disconnect the battery. There's 1.95 amps. We've gone over 100 watts at this point. I'm just going to nudge it to 2 amps and we'll leave it there. There we go, 2 amps. So we're back to what was stable on this unit when it was new. I suppose the next thing to do is to see if we can surpass the 2.25 amp failure point of this unit when it was new. I'm not excited about taking it there. I'm really not. But, you know, for science, it seems like that's what we need to do. The anticipation on my end is not enjoyable at the moment. I've seen this thing let out the smoke. This one and other models let out the smoke too many times, and there's nothing like knowing what's coming. But there we go. We have surpassed its original failure point. I am feeling heat in the heatsink at this point, and I'm happy about that. I'm happy to feel temperature there. That means it's conducting away heat from the MOSFET as it should be. 100 watts is a significant amount of power just to blow through some fans. So I'm happy with how it's working so far. Given this was originally rated at 180 watts, given that I don't trust that rating at all, given that I'm not excited about fixing this over and over again, and at some point I have to determine what I'm happy with. I think I would be happy with 150 watts. That would be 3 amps at 50 volts, which is significantly under the rating for the MOSFET and a totally usable unit for me. So I'm tempted to take this up to 3 amps and change to reach the 150 watt level. But I'll have to do it slowly and watch that case temperature. Okay, nothing to do but just to go ahead and do it. Let's dial this up a little bit. There's 2.5, let's hold there for a moment. Looks like our linear MOSFET is working well for us so far. Guaranteed safe operating area. Seems to be living up to its promise so far. Guess I'm getting my courage up here. We gotta find out if this thing's gonna fail. We'll have to take it a little bit over 3 to get to 150 watts. Fans have kind of shifted up a gear. Not sure why they didn't do that before. Give me 150. Ah, there's the 150 limit. It's actually disconnected things here. So at this point, I have to do something kind of funny. I don't want it to suddenly turn back on. So what I need to do is actually start at 0 and climb back up to that level. The limits are set here to basically disconnect the load, but what the very poor instructions that this comes with do emphasize is that you don't want the load to suddenly come on. You don't want to suddenly connect this to load. You want to ramp up. So they caution against like having these knobs up, for example, and plugging in a load. Well, if I canceled that alarm, that would cause this to turn back on and reconnect the load, and that might not be good. So the good news is we saw it hit 150 watts because we saw it hit the 150 watt limit. So I think I'll set that just up a couple watts, just so that we can leave it at 150 on the money for a little bit of time, and just make sure that that really does hold. We'll reconnect our battery, which is down at 51 volts now, and we'll slowly dial back up to about 3.2 amps. We'll actually turn to 3.26 so we can see a solid 151. It's nice to see that with replacement of one single component, in this case about 14 bucks plus shipping, I think it was, you can get this thing at least in the neighborhood of what it was originally rated at. Now, it may be able to go much further than it was originally rated at. Unfortunately, I'm too chicken tonight to find that out.
4 to 6 weeks later.
I just really want to know if this can take more wattage than it could as originally built. So I've gone ahead and set the wattage limit up to 210 watts. I'm going to go right into it. There's 3 amps, and at the higher voltage than I had before, at 55 volts, we're already up to 163 watts, which is more than I've tested this thing with before, and so far so good. I'd like to take it next up to 180 watts, which is what this was originally rated for, and see how it likes that. There we go. There's 179 watts. Temperature's at 52 C, so definitely getting toasty. Seems to be okay. Let's watch that temperature. It's at 57 C. I'd like to see it flatten out and hold. It's been running for 7 minutes here, and the temperature looks like it's stabilized at about 64 C. I'm going to dial this up to keep it just at 180 watts. There's about 181 watts. 65 C works out to about 150 degrees Fahrenheit, which is hot to you and I, but as far as electronics go, it's not that crazy to have 150 degree temperature in and around the MOSFET. So I've got my fire extinguisher ready. Let's go ahead and crank it up to 200 watts, see what happens. 185, 192, there's 201, 201 watts. And the thermal image camera says, well, it says it's good and hot. Case temperature for the MOSFET has risen up to 71 C. So definitely climbing. The question is, does it stabilize, or does it climb until failure? As the voltage in the battery drops, the current needs to go up to compensate for the same total wattage. So here we are, we're at over 4 amps and just a tick over 202 watts and holding steady at 73 degrees C. We're at 74 C now, or 165 degrees Fahrenheit. Well, we're coming up on 16 minutes of discharging this battery, much of that at the 4 amp, roughly 200 watt level. So I'm going to call the test complete because the temperature looks like it is stabilized at around 73 degrees centigrade. So I'm going to turn down the current, and I'm going to quickly turn this over and see if I can grab some measurements from the outside of what sort of temperatures we're reaching. Whoops, better not grab the fan. So here's the underneath of it. Of course, the fan is still running because the temperature is still up, but I've set my FLIR camera to centigrade as well. Celsius, centigrade, whatever you prefer. I'm just some American that uses the Fahrenheit scale. If I just point right at the bottom of the board underneath where that MOSFET is, 48 by my measurement, and 40, there we go, 48 also at the same time as the measurement on screen. So I'm thrilled with the performance on this. Of course, this was rated at 180 watts initially, and we just ran it at 200 watts for a sustained amount of time, most of it above the 50 volt and 4 amp thresholds, and a stable temperature at about 73 degrees C on the MOSFET case temperature. I'm really satisfied with that, to actually be able to exceed what it originally came with, and it's going to be really useful for many projects to come. So if you're still here watching at this point in the video, thanks for sticking with it. Thanks for watching. I hope this was really helpful to anyone else that has one of these types of units and is interested in upgrading it and making it more and more useful. If you have any questions, feel free to throw them down there in the comments. And if you feel inclined, go ahead and hit the like button. But most of all, thanks for watching.